Hey folks, so last time we talked about telescopes and the different types of telescopes. We talked about how there were two different kinds of telescopes, the reflecting telescope that uses mirrors and the refracting telescope that uses lenses. Talked about some of the advantages and disadvantages of each, and then decided that for a lot of cases, unless I really need a high magnification, I would probably want to use a reflecting telescope. That refracting telescopes can be really good for looking at planets or things like that, things that are fairly bright. But for a lot of cases, I'm going to want that reflecting telescope. Well, no matter what kind of telescope you have, you've got to use something to point it on. So we need some sort of mount that it can sit on. For your eyes, the mount is literally your head. You turn it however you need to go and you can see it. But we need something else for the telescope. And it turns out, just like there's two different kinds of telescopes, there are also two different kinds of mounts. The important thing to remember here, though, is that any telescope can be used on any mount. Don't be thinking that only one telescope goes with one mount. The second thing that we'll have to talk about is what kind of detector are we going to use? Now, the simplest detector we're going to see is just your eye, right? You put your Mark 1 eyeball to the eyepiece and you see. But it's got some disadvantages, and we'll talk about that as it comes in. So, what other kinds of detectors are there? And just like the mounts, I can use any detector with any telescope and with any mount. Don't think that any particular one is assigned to a particular one. You can mix and match all three of those things. All right, let's get started. Go ahead and have your class notes out. Front side's going to look something like this. Remember that it's two-sided as always. Pause the video till you've got that ready to go. All right, let's get underway. So we talked about how if we've got a telescope, we're going to need something to point that telescope. So this is an example of probably the simplest mount that you could possibly imagine. This is a tripod, obviously. It's not just used for telescopes. It's used for cameras. It's used for binoculars, all sorts of things. This particular tripod has a little knob that you turn here. And all that's doing is just allowing you to very slowly and precisely move it in the left and right direction. There's a separate knob up here that we can use for tilting it up and down, but it's the simplest possible mount you could have. So this type of mount is called an alt-az mount because it's tied to that altitude and azimuth coordinate systems. So the altitude is the distance above the horizon. So you start at the horizon at 0 and you go up and down. Azimuth is the distance around the horizon. You probably know it as north, south, east, west, things like that. So left, right is going to be my alt-az mount. So in this case, the tripod, I'm literally going up and down, left and right. But if you look at that tripod, you can probably see that you're not going to be able to put one of these big honker telescopes like we've got right here on one of these measly little tripods. It's going to fall over. It's not going to be very stable. And that problem has been around for a long time. And it was actually solved by a monk in San Francisco whose name was John Dobson. And he's actually a former monk because he got kicked out of the monastery because he kept sneaking over the wall to build telescopes. But he needed a way to mount very large telescopes. But he's a monk, he doesn't have any money. So the system he came up with, which is now called a Dobsonian mount, it's still an alt-az mount, but basically it's got this little swing mechanism. So the telescope literally just sits on this little wedge that you've got right here. And then so it's able to go up and down. And then it's sitting on a lazy Susan, if you've ever seen one of those, little plates that you turn. So it swings back and forth. It tilts up and down. There's no hinges. There's no nothing. It's just literally just sitting there. Sometimes it won't even be sealed in here. It'll just have a little notch that the mount on the side of the telescope just sits in from that. So it can just swing up and down, left and right. And it's beautiful. And you can make these things actually very big. In fact, I've seen some Dobsonian mounts with telescopes that were so big that you had to have a stepladder to actually get up to put your eye at the eyepiece here. And it's perfectly stable. It's also very cheap. You can build this mount for maybe $10. So remember, he's a monk. He didn't have any money. So this is the type of mount that we actually have on the telescopes that you can check out from GCC. The reason is because they're rugged. They're very sturdy. They're cheap. You're going to have a hard time damaging it. Don't try, okay? But it's going to be able to withstand a little bit of punishment from that. So the disadvantage to this is that it does just go left and right and up and down. But let's think about how things rise and set in the sky. So, for example, everything rises in the east and it sets in the west because they're not moving, you are. So the sun rises in the east, the moon rises in the east, the stars rise in the east, the planets rise in the east, everything rises in the east. But that means, if you think about it, it rises over in the east, but it reaches a maximum in the south. So I'm having to change not only my left right, my azimuth, but also my up down, my altitude. And then it'll reach a maximum in the south, and then it'll come back down and it'll set in the west. So if I want to take a picture of the sky, usually what we do, because the stars are so faint, what we'll do is we'll leave the shutter open on the camera. So it's just continually getting light, 5, 10 minutes, something like that. So as long as I've got it pointed at the star and that light keeps shining at the same spot, then that camera image gets brighter and brighter and brighter. And so I can actually see things that I couldn't see even with my naked eye through the telescope. Well, that's really handy. The problem with this, though, is that the thing is moving in two directions. So you've got to adjust it very precisely in both altitude and azimuth. And if you ever played with an Etch-a-Sketch, with the two knobs, if you ever try to draw a diagonal line with an Etch-a-Sketch, it's actually really crazy hard. And the problem with this is if you're trying to take a picture and you're trying to follow it across the sky for 5 or 10 minutes, if you're off by even a tiniest bit, your nice, bright, beautiful star now becomes a big smear from that. So these types of mounts are useless for astrophotography. If you're wanting to take a picture of the sky, you cannot use an Alt-Az mount. Now, John Dobson would say, why do you want to take a picture of the sky? All the good pictures were taken 20 years ago from Mauna Kea. Put your Mark 1 eyeball to the telescope and look at the stars, right? Because if all you're going to do is you're going to look at the sky, if you want to experience space and you want to see it with your naked eye, then this is what you need. It's cheap. Instead of putting all that money into a mount, put the money into a bigger telescope. Then you'll be able to see even more stuff. Because remember, the bigger the telescope, the more light it's going to gather, and the fainter the objects you're going to see. On the other hand, what if you do want to do astrophotography? I mean, I'm a research astronomer. I need to take data. I need to take pictures and things like that. So this type of mount, even though it's the perfect mount for everything else, is useless if I want to do astrophotography. So I need a mount that's going to follow things across the sky. And that's called an equatorial mount. So the way an equatorial mount works, and this is a lot easier if we're in person. I've got one that I can actually show you. But take a look at this one right here. It's sitting on a tripod, but that's not actually the important part. This part right here is called a wedge. And so this wedge mount has the telescope sit at an angle. So the telescope is free to turn like this. So do you see that it can follow the sky because it's only going to turn in one direction. So if my fist is the wedge and then my hand is the telescope. So it starts out, it's pointed towards the east. But as I turn, do you see that I'm very naturally getting higher in the sky and pointing south? And then if I keep going, because I'm going to break a wrist if I keep trying to do that, it's going to set and it'll follow it all the way across. So the beauty about these are that you only have to turn them in one axis. So what we do is we put a motor called a clock drive that turns at exactly the same speed as the Earth, but in the opposite direction. So as the Earth turns this way from west to east, the telescope motor is turning the telescope from east to west so that it always stays pointed at that star, exactly at the star. In fact, if you keep going for 24 hours, it'll eventually be pointed straight down because the star is on the other side of the planet. The Earth is turned, so the star is on the other side of the planet. So these things are perfect for following things across the sky. Now I want to caution you, it only corrects for the motion of the Earth. If you have something that's actually moving across the sky, like an asteroid or a comet, something that you can actually see moving, this will not follow it because it's only got that clock drive that's correcting for the Earth's motion. But for a lot of things, that's really all you need because it's going to follow it very precisely. And you can sit there and just take those pictures 5-10 minutes because you're following it without you having to even lift a finger. No Etch-a-Sketch magic knobs or anything like that. So this type of mount is actually really good for doing research. And you see there's actually a little camera actually attached to the back of the telescope right here. So this is another variation on, this is called a fork mount because the telescope right here, this part that attaches to the wedge kind of looks like a fork. So it sits like this and the telescope sits in between it. The other type over here, this is called a German equatorial. And it works similarly. It's still got the wedge. The wedge is actually right here on this pillar. This guy has actually mounted this in his backyard permanently. But then the telescope sits on one side of a bar, and then there's a counterweight on the other side, so that it still moves like this. And so it's still able to follow things across the sky. Now, the big disadvantage to this is if you get a big telescope, you're going to start to weigh down that bar right there. It's going to start to vibrate a little bit. And so you get a little bit of shake in your pictures, which once the telescope gets too big, that's really not going to be a good way to do it. So in general, these fork mounts are what's preferred. And this is what we have up at GCC North Observatory. So all of our research telescopes are mounted on these equatorial fork mounts that you see right here. So let's flip over to the next page. So look up at the top of your page there. Let's think about some of the advantages and the disadvantages of the Altaz mount compared to the equatorial mount. So, oops, lost my page there. Here we go. So, the biggest advantage, there's two really big advantages to the Altaz mount. The first is it's cheap. That mount, that Altaz mount, that Dobsonian mount I showed you, like I said, 10, 20 bucks max. Just you build it on a scrap lumber and you're good to go. The equatorial mount that I showed you might cost $3,000. The telescope probably only costs $3,000, and that mount is costing just as much. Now, imagine how big a telescope you could get if instead of spending $3,000 on that telescope, you spend $6,000 on that telescope. Or let's say you're not rich. If you've only got, $1,000 or whatever, you buy a medium-sized telescope, you put it on that Dobsonian mount that costs you next to nothing, and then you've got a perfectly good system. On the other hand, if you want to take pictures, you don't have a choice. You've got to use that expensive equatorial mount. So the big advantage to the Altaz mount is it's cheap, it's rugged. The disadvantage is it won't follow things. It won't track the sky. The equatorial mount is actually just the opposite. Its biggest advantage, in fact, its only advantage, is that it will follow things across the sky. There is no other reason really to use one other than, if you're rich enough, you have one, you can, for convenience. So it just automatically follows it. The disadvantage to it is, one, they're very, very expensive. Second of all, they are actually a little fragile. Now, not fragile in the sense that they'll get broken, but they have to be aligned perfectly to the North Star for that to work. Let's go back to our picture here. If you think about it, so we assumed that the Earth was turning this way, and so the North Star would be back in this direction, and this way it's facing south. If you put this backwards, or let's say we actually face east, now it's no longer going to follow things. Things are going to be rising this way, but the mount is going to be tracking in the wrong direction. So it can take an hour or more, sometimes 2 hours, to actually get this thing to be exactly aligned to the North Star so that it will follow the Earth as it should. And to help with this at the observatory, I designed a series of pillars, basically, that the telescope has pegs that the telescope drops down on, so that if you just drop it down onto the pegs, you will be mostly aligned to the North Star. And for most operations, it's good enough. It's quite close. On the other hand, sometimes if you need to do really precision work, like when we're trying to detect alien planets, you need to have it extremely precise, and so you're still going to have to spend that hour or two or more actually getting everything lined up before you can take any kind of observations at all with that. So that is a big disadvantage. Now, one thing we will, just as a side note, we will often still use our equatorial mounts when we're doing shows, not because we need it, because people are just putting their eye to it. We could do that with a Dobsonian; it'd be perfectly fine. But we'd have to periodically bump the telescope because it's not following things around. So we need to say, okay, let me get that aligned up for you. Okay, now take a look. And of course, they're going to see the object moving through the field of view. This way, if I've got this big long line of people, the telescope is following it. So when the next person comes up, the object is still centered in the eyepiece, and then they can use it. But that's more of a convenience thing because we do shows. It's not something really that you would be necessarily concerned about for your own use. So advantages, make sure you're copying these down into your class notes. For the Altaz mount, the big advantage is it's cheap and it's rugged. The disadvantage, it won't track the sky. The advantage of the equatorial mount is it will track the sky, but the disadvantage is it's expensive and it's hard to align. And the other problem is, let's say you finally get it aligned, somebody comes along and bumps the telescope, you just lost your alignment. Now you've got to spend another hour or two getting it back from that. So it's kind of fragile in that sense. All right, so remember that any mount can be used with any telescope. You can put on you can put a reflecting telescope on an ALTAS. You can put a refracting scope on an ALTAS. You can put a reflecting on an equatorial. You can put a refracting on an equatorial. The next thing we need to talk about is detectors then. So the eye, your Mark 1 eyeball there, is the very simplest detector. I mean, your mommy and daddy gave you two perfectly good ones when you were born. You've been using them pretty much all your life. You're probably pretty competent with how they're used from that. But it has some disadvantages. One of the big disadvantages to the eye is, of course, it doesn't make a permanent record. And you may have a photographic memory, but you probably can't make a print out of it. So if you're wanting to do some science, you usually need to have some sort of a permanent record, some data that you've gathered from that. And we didn't have a way to make a permanent record until just a couple hundred years ago. So prior to that, people would actually look through the telescope and they'd sketch what they saw. Well, if you're like me and you can't draw, then you're basically screwed. You're not going to be a scientist. You're not going to be an observer because you have to actually draw as precisely as you possibly can. And so that's a disadvantage. One big advantage though, it doesn't require power. You're probably not a robot, so it doesn't require power. You're not going to leave it at home. It's always there and you're getting to experience it. It also has another disadvantage though that's maybe not quite so commonly understood. Your eye is what we call a nonlinear detector. Let me explain what I mean by that. So if something is nonlinear, then in order for it to appear twice as bright, I might need 10 times as much energy coming in. So it takes 10 times that amount of energy just to make it look twice as bright in my eye. So that's a nonlinear detector. If it's linear, then if I've got 10 times as much energy, it's actually 10 times as bright. Or if I only want it to be twice as bright, then I only need twice the energy to make that work. So your eye is a nonlinear detector, which means you can't see the faintest objects with it because it takes exponentially more brightness for it to seem more energy for it to seem brighter to your eye from that. So that's a bit of a disadvantage. The next most common is a digital camera, which is technically called a CCD. You can win bar bets this way. A digital camera is called a charge coupled device. So that's the little chip that's on the inside here. And you probably all have used a CCD before because you've got a cell phone. Pretty much all of the cell phones that are out there nowadays have some sort of CCD camera built into it. And I've even seen people try to use these with astronomical things. They'll put the lens of the camera right above the eyepiece, and sometimes you can snap a pretty decent picture as long as it's one that you can just take an instant. It's not one that you can follow, of course, but if you just need like take a moon or Saturn or something like that, you can take a quick picture and it works pretty well. The reason these things have a couple of advantages: first of all, obviously it's a permanent record, so having that permanent record allows you to do data. A film camera will do the same thing. So you said, well, why wouldn't we use a digital camera instead of a film camera? Is it because we can easily put it on the computer? No, that's actually not why. A film camera is nonlinear, just like your eye is. So that means for the film camera, it takes 10 times the energy to look twice as bright. A digital camera, however, is linear. So that means if I can only get twice as much brightness, twice as much energy, it's actually going to look twice as bright. I don't need that 10 times as much energy from that. And this is what makes urban astronomy possible, because we can actually gather that light. It's sensitive to the light, so even the city lights won't wash it out. And I'm able to actually see things in the sky that I couldn't be able to see with a film camera. So you can take this very same telescope, take the eyepiece off and put a digital camera on it, put a CCD camera on it, and you can actually see much, much fainter objects without changing the telescope that's there. So that's a real boon. Now, the biggest disadvantage to this is that you have to keep a CCD camera cold. And you may say, wait a minute, Kayla, what's that about? I don't have to keep my cell phone cold at all. Well, actually, you probably have noticed if you've ever tried taking a picture at night, you ever tried taking a picture in the dark, how it comes out kind of grainy? There'll be that kind of oftentimes green colored grain that's in that. That's actually noise in the chip. That's heat coming into the CCD chip as it enters into the camera here. So whenever the CCD chip is not only sensitive to light, it's also sensitive to heat. So that's going to make it give these false kind of grainy images that you're going to see. Well, most of the time during the day, the amount of noise from heat is only going to be maybe that much, but the amount of light that you're getting is going to be this much. so you don't notice it. Takes a perfectly fine picture. If you're in the dark, though, now you've only got this much light and you've got this much noise, and so now you can see it. Well, in astronomy, it's always dark because we're always taking pictures at night. Well, that's not acceptable to have all of that noise because now those sparkles start to look like stars. You're not going to be able to tell what's a star and what's just the random camera noise. So for that reason, we have to keep the camera very, very cold. And then if you look on here, the chip, the CCD camera itself, is actually just a tiny little square right here. This is just the mount that goes into the eyepiece mount of the telescope. The rest of this is actually a cooling system. So what it's doing, there's a heat sink that's attached to the camera, to the chip, that pulls the heat out of the chip. And then this has a big fan in it that pulls that fan and exhausts the air out. And we can actually we can take this camera up to the observatory at night and we can get the temperature of the chip down to about 0 degrees Fahrenheit. So about just a little bit, I'm sorry, 0 degrees Celsius, which is about freezing, 32 degrees Fahrenheit for that. So we can get it quite cold. And if you really are doing precision work, some people have even developed systems where they run liquid nitrogen around the chip to get it crazy cold. And then you can get rid of pretty much all the noise, even if you're taking a picture at night. So that is a disadvantage. A film camera, you don't have to keep cold like that, but it's nonlinear. Here, it's a linear detector, but you do have to keep it cold. But the advantage of having that linear detector way far outweighs the need to keep it cold. So this pretty much all astronomical pictures these days are done with a CCD camera. Another type of detector we have is called a spectroscope, and the whole purpose of that is to make rainbows. So this actually goes in between the eyepiece, either your eye or the camera, as the case may be. And you can kind of see it right here. This is called a diffraction grating. If you've ever seen these rainbow glasses, where you look through and you see these rainbow colors and things, that's what this is. It's taking the light and it's spreading it out into its component colors. You might say, well, why would you want to do that? Well, we're going to be doing a lot of spectroscopy. We're working with a spectroscope a lot this semester because that rainbow will have what we call absorption lines in it. You'll learn about these later. But if this is the light from the star and I see this particular pattern of lines, that tells me there's hydrogen present. If I see this pattern of lines, that tells me there's helium present. If I see this pattern of lines, it's carbon, and so on and so on. So by looking at the spectrum that you see in here, and then teasing out which of these lines go with which element, I can figure out what elements are present in the star. And you remember how we talked about at the beginning, if I know what elements are in the star, I know what elements are on the planet. If I know what elements are on the planet, I know what elements the alien is made out of. So this is one of the main ways we're going to figure out what those aliens are made out of, is by doing this kind of spectroscopy. So we'll talk more about that later, but that's basically what it's there for. The fourth method that we use is called a timing measurement. Now, usually we're going to use a CCD with this. We're going to use a CCD to record it, but this is not a CCD picture. Instead, we take a picture of it and then we use an instrument, a computer sometimes, to measure the brightness at that particular time. And so then we just plot that on a graph. So this is actually a graph. So each dot represents one CCD picture. So the timing measurement is not a separate instrument. I'm using that CCD camera to take a bunch of pictures rather than just one. And so here you can see that this was the picture of the star. And yeah, there was some variation. This is noise. There's always noise in your data. But overall, the brightness of the star was pretty constant. And then something happened, and the brightness of the star dimmed for a little period, and then it came back up from that. Well, we talked about that at the beginning. This is a planet moving in front of its star. So this is what it actually looks like when you see an alien planet move in front of the star. The planet moves in front, it blocks some of the light, and so the light dips until the planet moves off. So you're actually seeing that planet transit across the surface of the star. So to measure that, I'm measuring timing. So when you're thinking about if something's changing over time, you're probably doing a timing measurement. So it's not the instrument that you're using, it's how you're using that instrument. So what I want you to do now is I want you to pause the video, look on the back page here, of second page of your class notes. I want you to match the detector to the task that you're trying to do. So pause the video and do that now. Did you pause the video? Pause the video. Okay, so let's look at that. So So our first detector is the eye, and figure out where my mouse is. Here we go. So our choices are permanent image, measures composition, temperature, and velocity, measures changes in brightness, or it's free, always available, but doesn't have a permanent image. What do you think? Yep, it's always going to be available, and it does not make a permanent image. So that one goes right there. All right, how about the CCD camera? So if you look at that, it's got the permanent image. It's not really talking about measuring composition. It's not measuring changes necessarily. So that's going to be this one. And notice that we can also measure color with the proper filters. I'm going to talk about that more here in just a second. The spectrometer, what's it for? We talked about how it's going to measure the composition. And then the box here is telling you some more things that we're going to learn to measure. You're going to measure the temperature of the star and the velocity of the star, how fast that star is moving. So all three of these things you're going to do as part of this class. And then, of course, then the last one is timing. And the key thing here is we're measuring changes in brightness. That's what's giving you the clue that it's a timing measurement. So your class notes should look something like this. Okay. All right, so I mentioned that with the right filters, we can tell the color. Did you know there's no such thing as a color digital camera? It's true. They don't exist. But, Kilo, I've got a cell phone and it's got a color camera, right? Well, no, not exactly. Every CCD camera is a black and white camera. It's a grayscale camera, all of them. However, what we do is we put a filter over it. So we put a blue filter over one image, a green filter over the other, and a red filter over the other. So you've actually got 3 CCDs inside this phone. You've actually got 3 cameras running all at the same time. So the blue filter only allows blue light to come in. The green filter only allows green light to come in. The red filter only allows red light to come in. But when I mix these together, that's when I get a full color image. If you've ever seen a projection screen TV, that's how they work. And if you ever haven't seen one, go up to Best Buy and pretend like you want to buy one, and they'll show you one. But there's a blue lamp, a green lamp, and a red lamp. You may have heard of an RGB monitor, red, green, blue. You shine those together then, and you get the full color image from that. So that's what we do with this digital camera. It's actually black and white, but it's coming out. It's only allowing the blue light, only allowing the green light, and only allowing the red light. So this is what your camera actually sees. One of these pictures was taken through a blue light, through a blue lens, the blue filter. One was taken through a green filter, and one was taken through a red filter. Now, the important thing to remember about a CCD is the more light it receives, the whiter it becomes. So dark means it did not get much of that color. White means it got a lot of that color. All 3 of these pictures were taken at the same time, and this was taken down by my house. So if you can figure out where this was, then you know where I live. Good luck with that. But so one of these was taken through red, one was taken through green, and one was taken through blue. So you could look at your class notes and cheat. Don't do that. Put them away. See if you can figure it out. So which one, look at this picture right here. What filter was it taken through? Well, the stop sign is red, so it appears whitest in red, right? So we take that picture then. So this must have been taken through the red filter. All right, so one of these is blue and one of these is green. What do you think? Well, there's 2 ways you could do this. The palm tree here is obviously green, and you see how it's brighter in the middle picture than it is in this one? That means that this must have been taken through the green filter. The other way you could look at it is you look at the sky. Here in Arizona, we have blue skies pretty much all the time. So the sky is brighter in this picture than it is in this one. So this must have been taken through the blue. So this is red, this is green, and this is blue. But this is what the camera actually sees. It sees it as black and white. So then what we do is we tell the computer inside your camera, inside your phone, we say, okay, instead of coloring this from black to white, color it from black to red. And for this one, instead of coloring it from black to white, color it from black to green. For this one, instead of coloring from black to red, color it from black to blue. And now we take all 3 of these and we blend them together, and I get my full color picture from that. So this works really well with the camera, but there's actually 3 cameras in here. All 3 black and white cameras, but each one has a filter over it so that you get all 3 colors at the same time. Now, In astronomy, we don't actually need 3 different cameras because remember, we've got our equatorial mount. We're following it across the sky, and the stars and galaxies and things aren't going anywhere. So I can take one picture in red, take another picture in blue, take another picture in green, color them in the computer, mix them, and I get the full color image like we showed you. So that means that from almost all astronomical CCDs are actually single black and white CCDs because you just don't need it. And so what we do is we have a filter wheel in between the camera and the telescope, and we can control that actually from the computer. You hit a button and it'll flip that blue filter in, and then it'll rotate and it'll flip the red one in, and then it'll flip the green one in, and then you combine them in your computer and you've got your color image. So why pay for the 2 other cameras that you don't actually need? This allows you to have a pretty cheap but extremely sensitive CCD camera for astronomy. Now, you might wonder, well, why wouldn't we do that for this? Well, obviously, if I'm trying to take a picture of my 14-year-old who's going like this or whatever, I'm not going to be able to get her to completely freeze each time so that I can take, okay, one in red, one in green, one in blue. And then when I try to put them together, of course, they're not going to match up. So with the cell phone camera and most digital cameras, you're just going to take all 3 pictures at the same instant. That way you can combine them automatically. You've got your color picture. Okay, so that's it for this one. You're going to download your mounts and detectors practice worksheet, fill it out as always, scan it, or take a picture with your color digital camera, and then upload it up to Canvas. Don't forget that these are going to be graded for accuracy. Okay, guys, so I want to stress, and I've said this several times, but I want to stress with you, you can use any detector with any mount and with any telescope. A lot of times people will say, oh, I can only use a CCD camera with an equatorial mount because the equatorial mount is the one that's going to track. Not necessarily. You can use that CCD camera with an alt-az mount. Just make sure that you're taking an instant picture so that you don't need to follow anything. So for example, the moon is very bright. You don't want to take a long exposure picture for that. If you sit there and just follow it across, you're just going to wash out the whole picture. So you're just going to go snap. An alt-az mount is perfect for that. You don't need it. But in general, if I'm going to take a picture, that's a clue that you're going to need that equatorial mount for that. But there's nothing mechanically stopping you from using one with the other. So one of the things we're going to ask you to do is we're going to give you a situation. You're going to do this in lab. We're going to give you a situation and we're going to say, okay, here's what we've got. You decide what mount, what detector, what eyepiece, and what telescope do you want to use for this particular situation. You're going to have to justify your answer with that. And you're mostly being graded on your justification for that. All right. So if you have any problems, be sure and come by Live Help because this is one where you really got to kind of think about it. It's not just an automatic, oh, I'm going to look up in my notes what I need and go straight from that. You have to really understand those advantages and disadvantages and then apply them to the particular situation. All right. We'll see you next time.